Let's say that the school inspector wants to find out if it's warm enough in the school. So let X be the temperature in the classroom in the school. And assume that classroom has an expectation value of the temperature in degrees of Celsius and a known standard deviation of 1 degree Celsius. If the expectation value of the temperature is larger than or equal to 20 degrees, then we say the school is warm. And if the expectation value of the temperature is less than 20 degrees, we say it's cold. So the border between warm and cold is 20 degrees. Let's say we have measured the temperature in 10 classrooms, and that has given a mean of 19 degrees Celsius. This sample indicates that the temperature is cold in the school, but we cannot be sure because also a warm school could give this mean temperature. What the inspector really wants to find out is the probability that the school is cold, given that the sample is 19 degrees. However, it's not very easy to calculate this probability, since it depends on what kind of background information we have. Therefore, statisticians instead calculate this probability here, the probability to get a sample of less than or equal to 19 degrees, given that the school is warm. And the reason giving less than equal here is because being equal to exactly 19 degrees, the probability for that will be 0. If this probability is small, then it's very unlikely that the school is warm, which means that it is probable that the school is cold. However, the problem is that also this probability involves background information, which makes it difficult to calculate. However, you can show that this probability is less than or equal to the probability to get a sample temperature of less than 19 degrees, given that the temperature is just at the border between warm and cold. This probability can also be written more succinctly in mathematical symbols, like this. So the probability that the sample mean is less than or equal to 19, given that the temperature is equal to 20. This probability here, statisticians call a p-value. So this is the p-value for this situation. And if this is small, that is, you have a small p-value, that means that it's unlikely that a warm school will give the sample we got. So if the p-value is small, that means it's likely that the school is cold. And this probability we can calculate. Assume that the mean of the sample is normal distributed, either because x is or because n is larger than or equal to 30. And here we assume the first case, since we assumed at n equals to 10 in this case. Let's change this normally distributed random variable to a standard normal random variable set. Then we have that this is equal to 19 minus the expectation value divided by the standard deviation divided by the square root of n, given that the expectation value is 20 degrees. Since this says here that it's given that it's 20 degrees, we can replace this with 20 here, and at the same time remove this part. And then we can also replace this by 1, since that was given, and this with square root of 10. And this here is roughly equal to minus 3.16. And by symmetry we have that this is equal to this, which according to the probability table is equal to 0.08%. Since this is a very small probability, that means that it's very unlikely that the school is warm. That means that it's very likely that the school is cold. So to sum up, given that the school is warm, the probability is at most 0.08% to get this sample that we got, or even colder temperature. One says that the school is cold with a p-value of 0.08%. Let us look a little bit closer what the p-value really tells us. So assume that we have the situation in this figure. Given that the school is warm, the probability is only 1% that the sample shows that the school is cold. And is the school cold, then it's 99% likely that the sample shows that the school is cold. Then, if we get this sample that tells us that the school is cold, what is the probability that the school is cold? Perhaps it seems obvious that this must be a large probability. But as we pointed out previously, This probability is actually difficult to decide, because it depends on what kind of background information you have. Assume that you have background information that says that it's equally likely that the school is warm as it is cold. Then, given that the sample tells us that the school is cold, then the probability calculation gives us that it's 99% likely that the school is cold. So in this case, it is a high probability for it being cold, given that we got a cold sample. However, assume that we instead have background information which says that it's unlikely that the school is cold. For example, there is 1% probability that it is cold and 99% probability that it is warm. Then, in this case, if the sample shows that the school is cold, then a probability calculation tells us that it's equally likely for the school to be warm as cold. So, in this case, despite it's very unlikely to get a cold sample from a warm school, it is just as likely that the school is warm as it is cold, given a sample that tells us that it is cold. So the conclusion is, even if it's unlikely to get a cold sample from a warm school, it still can be probable that the school is warm, depending on what kind of background information you have. So despite that the p-value was the small 0.08%, strictly seen, that doesn't mean that it's unlikely that the school is warm. However, if we assume that we have background information that tells us that the probability for the school to be warm is between 10 and 90%, then it's likely that the school is cold for such a low p-value as this. Since it's not very easy to quantify background information, therefore statisticians instead focus on the p-value, since that does not depend on what background information you have. However, one should be aware of that there is some limitations on how far drawn conclusions you can draw from a p-value. Assume that the army wants to buy parachutes. Then a factory produces parachutes that can withstand a load of X tons, and this has an unknown expectation value of mu tons, and a known standard deviation of 1 ton. Then the military has as a demand that the expectation value must be larger than 10 tons. So a factory is good according to the army if the expectation value is larger than 10 tons, and it's bad if it's less than 10 tons. A sample of 36 parachutes says that the parachutes can in mean withstand a load of 10.5 tons. Even though the sample indicates that the factory is a good one, also a bad factory can produce this mean. So the military can't be sure that the factory is good. The probability that the bad factory will give a sample larger than or equal to the one we got is this. And this probability is the largest when the factory is as good as it can get among those bad factories. So when the expectation value is equal to 10. So the factory is at the border between good and bad. So if we calculate this probability, where this is exactly 10, this gives us an upper limit on how large this probability can be. So this is how large probability this one can be. And this one here is the p-value for this situation. Since n is larger than or equal to 30, then the mean is normal distributed. So if we change to the standard normal distributed random variable set given by this, we can calculate this p-value. So if you change from this to set, then we have to change this to this. Now we can replace this one by 10, and at the same time drop the whole this, given that thing. Then we get this one here, which can be simplified to this. And according to the probability table, it's equal to 0.13%. So this is a very small p-value. That means that it's not likely that the bad factory gave us the mean we got. So we can with large probability conclude that the factory is good. So we say that we conclude that the factory is good with a p-value of 0.13%.